What's going on, guys? Welcome back to the channel. In today's video, I'm going to show you 3 different ways to create an AI computer player for our game Snake. So if you didn't watch the previous tutorial on my channel, I showed you how to create a Snake game in Python using the Pygame module, and I will add a card to that tutorial video as well as a link to it in the description and a link to the GitHub if you want to grab that code for this video. I'm not going to show you how to build the entire Snake game from scratch. We did that already. And in this one, we're going to focus on how to create a computerized player. Before I begin, thank you Coding Kasauri for the suggestion for this video. He said, hey, cool video. How about coding different AIs that can play the game perfectly, when I posted the initial how to build a simple Snake game video. So if you have an idea for what you'd like to see in a future video or any concept that you'd like covered, just let me know about in the comments below. Be sure to leave a like on the video, subscribe to the channel, helps me out a ton, and stay tuned to maybe see your suggestion in a future video. So when I dug into this a little bit and started creating a computerized player, I realized there's actually quite a few different ways you could have an AI that plays the game Snake. And there's actually a really simple way to build an AI that's technically going to get a perfect score every time. And it looks something like this. This is basically a version of Snake where the computer knows to just take the absolute longest route through the board. So no matter where the food is, it actually doesn't really care because it knows eventually it'll hit the food, and it'll know no matter how long its body gets to be, it'll be safely stored behind it until it gets the absolute maximum score. This is a super simple solution. It really only requires like 3 lines of code. Basically, start the game with the snake going upwards, and if you hit the top of the board, turn right and then go downwards, and if you hit the bottom of the board, turn right and then go upwards. And it'll do that the whole time. If you have a version of Snake like we do, where you can pass through walls, which is the traditional style of Snake, then this is all you have to do to get a perfect score. But this is, one, it's pretty slow. It looks basically nothing like how a player would play the game, so it's not exactly optimal. And it's kind of slow and it's kind of boring, and it doesn't really require a lot of coding knowledge, so we're not going to cover that anymore. That is the most basic way to get a Snake AI that's going to get a perfect score every time. And then the second kind of AI that this video is not going to cover is what would be considered like maybe more true AI, which would be like using a free agent where you don't give it any rules. You would want to use the PyTorch module for this, and essentially do reinforcement learning, or you basically introduce a little bot that has no idea about the world that it's in or anything. It just knows that high score is good, lower scores are bad, and you let it do thousands of iterations and learn what it has to do to get higher and higher scores. That's like machine learning level AI. I'm going to keep this a little more introductory, but if you are more interested in that style of AI and tutorial, there's a series by a YouTube channel called Python Engineer that I recommend you go and check out. He does a great job not only showing you how to create that sort of AI, but also explains a lot of the theory behind reinforcement learning. So I don't know him. He's not sponsoring the video or anything. It's a good series. So check that out if you want to as well. But what we're going to do in this video is show how to actually program a Snake AI that's going to act basically like a player and make decisions like the player would, and pursue food similarly to how a player would pursue food. So without any further ado, let's go ahead and get into the tutorial. All right, so we're starting here with the Python Pygame version of Snake that we built in the last video on the channel. Again, there will be a link to the GitHub for this code, as well as the tutorial itself on the channel in the description below. So if I don't have a card on the video right here, then just check out the description if you want this code. But this is what we're going to be starting from as we create an AI. So let's go ahead and get into it. So basically, any version of AI, we're going to want to take our Snake that we created in the previous game and basically get rid of its ability to control our movement, or give it the ability to control our movement, get rid of the player's ability to control the movement. So I'm just going to repurpose this handle keys function because we already created a spot that was supposed to control the snake's movement. We just called snake.handleKeys every iteration of our loop. So we'll go ahead and remove the spot where the player can tell the snake how to turn. And we're going to start creating some logic for the snake playing on its own. So first thing we want to do, I'm just going to get the snake's head position right at the beginning, which again, if you aren't familiar with the different functions we put in this snake class, you may want to consider checking out the first video or just follow along and understand there's going to be some code written already that maybe you can pick up as we go along, or you're going to want the explanation. So we're going to get the head position, which is going to give us where the head of the snake is as an X and Y coordinate. And we're going to want to compare that to the food's position. So what I think we should do is pass in, when we do handle keys, pass in the food's position, which will be easy enough. We just go down to where snake.handleKeys and we add food.position. So we already had the food's position as a XY coordinate from the previous tutorial. We just want to pass this into the handle keys function now. All right, and then the basic first step of the AI is going to be make sure the snake understands where its head is relative to the food and pursue it. So figure out how to get closer to it. And to do that, I propose we start by creating a tuple variable. So a set of coordinates, essentially a two-dimensional vector, that's going to tell us how far from the food in the X and Y direction we are. And to do that, I'm just going to do the X and Y coordinates of the head minus the matching X and Y coordinates of the food. And so basically you can look at this as if head, let's say, is further to the left than the food, this will be a positive value. And that'll tell us that we need to go right to find the food. And if the head's Y value is greater than the food position's Y value, that'll tell us that we need to go down. But if these are negative, then that means left or up, depending on obviously left and right. And so the simplest thing we can do would be just, excuse me, would be essentially this. If distance 0, so this is the X coordinate, is greater than 0, self.turn and go left. So this basically means we just checked the X coordinate and we are too far to the right. The food is to our left. And then we can do another if distance 0 is less than 0, then we want to do turn right. And you could also do these as elifs. I'll kind of explain why that's up to you in a second. I'm just going to copy these two real quick, and we're going to do basically the same thing for up and down. But now we're checking if distance 1, so this is the Y coordinate, if that's positive or negative. And if it's positive, because of the way the Pygame grid works, positive actually means that head is going to be further down. Let me make sure I got that right. Further down, because 0, 0 is in the top left of your screen in Pygame. So larger Y values are closer to the bottom of the screen. So if it's positive, we want to go up. And if it is negative, we want to go down. Okay? And honestly, just right here, what we did, you have the most basic version of a Pygame Python snake AI. So let's go ahead and run that just to take a look at what that does. Now, what we'll see after it gets a few points here is it's going to pursue the food in the most direct way it possibly can, but at the risk of its own body. So it will, at this point, drive into its own body, as it just did there, to get food because we haven't given it any other conditions and told it that that's bad. So another thing I'm going to do for this tutorial, down where we have clock.tick, controlling how fast the game moves, I'm going to step that up from 10 to 20. 20 should still be slow enough that we can view it to talk about it, but now it's going to move much faster because the computer's playing. It doesn't care about the speed. So you can see right there, it's pretty cool, actually. It makes decisions essentially like what a player would do, which is locate the food and go after it. But obviously, when it turns too rapidly after it gets to around the 20s, it destroys itself because it doesn't know that turning into its own body is bad. So I had this running on my version where I was also totalizing the total number of games and averaging the score. And just at this level, it gets to around 20, which is not difficult to do as an individual player. And so our goal, I think, would be get a score at least around what a decent player could get. So this is cool. It's basic, but let's go one step further, which would be warning it that it cannot turn into its own body. So basically, it will only make a turn if it's not going to hit itself. So let's start there. So what we want to do is come into the if statements for all of our distances. Oh, before we move on, I promised I'd say why these could be ifs or elifs. And basically, it's up to you if you want to. Just understand if you're in a situation where it needs to go left and it needs to go up, if you do it in this order, then it's always going to turn left or right before it turns up or down. So it's going to control which one gets precedent. If you do all of these ifs, it still kind of happens that way because it's going to come top down. That's how Python code works. So like, for example, if you have to go left and you have to get up to get to a piece of food, it's always going to be looking to check left before it checks up. It doesn't make a significant difference. I played around with the order of things and what they totaled for different versions of it. Doesn't make a significant difference to the score, but if you ever are watching it and you notice it always tries to pursue left and right before it does up and down, it's because of that. Okay, so what we want to do for the next step of the AI is we want to add a check to make sure that it won't turn into itself. And so this has to be a little bit customized for each turn. So what we want to do is add another condition before we let them turn left. And we want to include and head 0 minus and then grid size and then head 1 is not in self dot position. So we already have this list of everywhere that the body is currently occupying. And I know some people have mentioned they don't recommend putting like self dot positions list. They would just keep track of it on the board, like have a board of all zeros or -1. And when the body is currently in that spot, have an integer value that counts down, that's positive, and counts down how many more turns that spot's occupied. You could do that too. You would still have to check that the board was not occupied then, however you do it. But what we just said here is, okay, I think we want to turn left because the food is to the left, but I just checked and one grid to the left of where the head is right now is actually occupied. So this is saying both have to be true. The left space has to be unoccupied and the food has to be to our left. And so hopefully that makes sense. But we're going to copy that and do essentially that, but modify it for each turn now. So let's say for the right, it's going to be the same thing, but it's going to be head plus grid size. And the reason it's plus grid size is because these head 0 and head 1 are the X and Y coordinate for each square. So it's not just like 0, 1, 2, 3, 4 as you go across. It's whatever square you're at times the grid size, which in this case is like 20 because it's, I think, 480 wide. And we have 24 squares. So to check that the right square is not occupied, it's just the same formula but plus grid size. And then it's very close for up and down. It's just obviously instead of checking that left and right are not occupied, we're checking that up and down are not occupied. So it's head 1 minus grid size, and then the checking that it's open down is going to be head 1 plus grid size. And I think I have one too many space in here. Alrighty, so now this is not going to let you turn into your own body. So it's not telling it what else to do, but it is saying you're not allowed to turn into your own body. And we can go ahead and take a look at this. The most common way we were dying before was not actually turning into our own body, but it was not turning away when we hit our own body. So like occasionally you will take a turn that's not going to directly hit your own body, but 20 paces down the line, like it just happened there, you don't turn out of the way. So this is going to prevent, say you had your entire body curled in 2 consecutive columns, and I don't know if this randomly generated version is going to give us the scenario that I'm talking about. But if your entire body was folded in 2 consecutive rows, it wouldn't turn into itself, but it will turn in the direction of its body and eventually hit it. So again, I had, just with the change that we made, I let that one play out for quite a while. Oh, you can see just there, actually, it did what we needed it to do. I let that one play out as well for quite a few games, and it only improved the score from an average of about 20 to an average of about 23. So that's still not really ideal. It's definitely getting better, but this next change is going to actually get us up to about 35, 40. So that's what I really want to accomplish for this video. And the next chapter is going to be turning out of the way when you sense that the spot you're moving into is occupied by your body. So this is a really important one, and it's also a fair bit more coding intensive than the last 2 that we did. So let's go ahead and put it together. So what I want to do in our handle keys function, and this is significant enough code that you could definitely break it out into its own routine, but I want to create a new loop every time we check this to see how big of a if we are about to collide in the left or right directions. So to do that, I want to say I'm going to create a new variable that we'll just use locally, so you don't have to do self.colliding. You can just say colliding. But what I want to check is if self.direction is equal to down. So this means we're moving downward, and now, similarly to what we did down below to check that it wasn't occupied before we turned, we're going to check that head 0 and then head 1 plus grid size. So it's literally just like the check we do before allowing the player to turn down. We want to check that that square is not occupied. So what we'll say is if we're heading down and the next square is occupied, so in self.positions, then we're going to take this colliding variable and set it equal to down. And then we're going to copy this exact code and do it 4 times. Here, so if we're heading upwards and the square above us, above our head, is occupied, then we're going to say that we'll be colliding upward. And we'll use this to turn left or right in just a second. So then we want to do the same for left and right. So we'll say left, and then we'll say right. And then we're going to make the colliding instruction left, and then we'll say colliding right. And we are going to get these grid sizes. So if we're heading right and the next spot to the right is occupied, then we'll say we're colliding the right. And if the next spot to the left, then we'll say colliding left. And I put too many spaces there. Okay, so this should tell us if we're colliding left, right, up, or down in the direction that we're moving. But what we need to do now is make the decision to turn out of it when we get that information. And so to do that, we're going to go down to where we were already controlling whether to turn left or right. And I'll show you the simplest way to incorporate this, but then I'll also show you how to make it better, as we've been doing this whole video. So the way to incorporate this step now into our decision-making matrix is, let's say that we're colliding up or down. Then we don't actually really care too much. We want to make sure still that this is true, so we're not turning into ourselves. But now we're going to add an or statement to this guy. So this guy is saying that, well, the main scenario where we'd want to be turning is if we're pursuing food, but we're going to say or, and then in here we're going to add some new conditions. Colliding is equal to up, or colliding is equal to down, and you're probably saying that doesn't make perfect sense because, well, what about turning right? And that's why I said we're going to get to just next. So I'm going to go ahead and basically copy this exact statement for up and down, and I'll just say that we're going to turn down for now. Turn down for what? Control V. So right now, if we sense collision left or right, we're going to just turn up. And then if we sense collision up or down, we'll turn to the left. So this should be a basic way of avoiding our own body, but it's not smart. It's just basic avoidance. So let's go ahead and take a look at what that looks like. And we'll just need to give it a second so it gets long enough to where it could hit its own body. But I'll point it out when I see it, hopefully around like the score of 20. Ordinarily, there's a turn where it would hit itself, and in this scenario, it should turn at least once out of the way. So you can see there and there, we get a few of these rapid little shifts, but if you saw why we just died there, it's because it wasn't calculating whether it was a better decision to shift to the left or shift to the right. Just no matter what, when it's about to hit itself, it was turning left and it was turning up. So the next step is making an intelligent decision about whether there's a larger gap to the right or to the left of it. And so to do that, we're going to come up above our collision detection. This is still correct. This is still good, but we're going to add something new that I'm going to basically call gap detection. And so I'm going to create these variables that are unnecessarily large. So left gap, right gap, and all I'm doing is when I'm initializing them, I'm giving them large values. We'll say top gap and bottom gap, and that'll be clear why in just a second here. So what we're going to do is we're going to say for I in range, and then we're going to say from 1 to integer of grid width. So this is saying, and you would want to do this separately for the X and Y for the left and right gaps than the top and bottom gaps if you didn't have a square board. We have a square board, so I'm going to use this exact loop here for top, bottom, left, and right, but you'll see what I'm talking about in a second. We're going to check that every square, not the player's head, which is why I'm not including 0 here. We're going to check that every square on the board, whether or not it would be occupied right now, and we're going to report those as the left and right gap. So let's just go ahead and get started so I don't have to talk. I can show you with code. What we're going to do first is calculate the top gap, so how much space we have above our head. And we'll say if the head square that we're in, so head 0, head 1, which is right where our head is, minus I times grid size, if that's in self.positions, self.positions, then we want to say that top gap is equal to I. So let me just reiterate what's going on here real quick. Actually, we want one more check. If top gap is less than I, because obviously if we find out that 2 spaces away we don't have a gap, but 3 spaces away we do have a gap, we don't want to overwrite. We want to find the closest position to the head. So let me kind of boot this up real quick so I can talk about what we're doing. So essentially looking at this grid, we want to iterate through the entire map and check for squares above the head, to the left of the head, to the right of the head, and below the head, and say how large of a gap you have before you hit a space that has your body in it, which is going to tell you how far you are from collision on that side. So what we're doing here is we're checking the square 1 above the head, 2 above the head, 3 above the head, and as soon as we find one that's equal to an occupied space, we can stop calculating there, which is the purpose of the if top gap is less than I, top gap is equal to I. And we're going to go ahead and copy that if statement for all of these calculations, and we're going to put it in here 4 times. All right. And so we'll say for calculating the bottom gap, it's going to be the same thing, but it's going to be plus I times grid size. And then if bottom gap is less than I, and that's why I give I 100 to start, because we're trying to calculate how big of a gap we have to the top and to the bottom. And then we're going to do the same to the X and the Y. And I don't think I finished that thought, but the reason I start all of them at 100 is because as soon as we find one that's like 2 squares away, 3 squares away, that'll always overwrite 100. If I were to put some dummy value in here, 0, or I could even say like the number of squares, which is 24, which is technically the farthest away anything could ever be. There's no reason to not make these huge values initially, so that once we hit something, for sure it'll get overwritten. Okay, so now we're checking if there's a gap to the left. And it's obviously pretty similar code for all 4 directions. And then here we'll be checking if there's a gap to the right. Okay, and now this is pretty easy to incorporate into our decision making. Because what we want to do now is say, okay, we're moving downward, or I think we want to turn left because the food is in the direction, or we're colliding upwards or downwards, but now we want to add a condition to this colliding bit here. So, or colliding up or colliding down, and pay special attention to the parentheses that we have here. So we're saying that if we're about to collide in the up or down direction and the left gap is greater than the right gap. So we're saying we have more space if we go left than we would if we went right. In that case, then we want to do the same thing as we would have before. So now we get to take this or statement and we can put the exact same or statement inside of our right turn logic. But this time we're just going to flip it to say, okay, we're about to collide up or down, and right gap is greater than left gap. And you want to pay special attention to this. It doesn't really matter which one you pick, but say they're equivalent. Say you've checked left and right and there's no collision. Then you're going to want to make one of these greater than or equal to. It doesn't actually matter a ton which one. Technically speaking, you could check whether you're further to the left or right of the board and make a decision there. But this is the simplest way to just make sure that if you're about to hit and the 2 gaps are equivalent, you still do one of them because you always want to turn out of the way. Okay. So now let's go ahead and do that to our up and down turns. So we're going to say or colliding, and then add an and statement in here. And this is to turn up. So we're going to say and top gap is greater than bottom gap. And I'll put the greater than or equals to first. Or. And then we're going to copy this whole thing. And if distance is 2, put it right before the and drop the or right in there. So if we're colliding in the left or right direction and the bottom gap is greater than, remove the equal sign, greater than the top gap, now we're going to turn down. So to really quickly review everything we're checking before we turn down, we're saying, okay, the food is somewhere below us on the board, or we're about to hit our own body in the left or right direction, and we've calculated that there's more space below us than above us, and we've calculated that the spot we're about to turn into is not in our self-dot positions. So this is pretty smart now, pretty smart AI. Let's go ahead and run it. Enough talking about it. And what you'll see, especially if you have this and you're following along on your own, this now is smart enough to average in the 30s. I don't know if we'll get lucky on our first game here and get a score in the 30s. But I let this one play, and I mean really play. I left it on like through dinner just to come back and see what kind of scores we had. And through 568 games, I was getting an average score of 36 with this bot, and that's crazy. Actually, I think we got exactly 36 on our first playthrough. But this is actually finally pretty satisfying to watch. It's making some intelligent decisions and quick movements, sort of similar to what a good player would do. It's turning to get out of its way. It's making an intelligent decision about which way to turn so that it gives itself more space. The next thing to do would be figure out how to calculate that gap and include the boundaries. So make sure that you get out of the way. After that, it would be adding some code to make sure that you don't turn into a trap. So like if your body is creating a horseshoe, you don't want to turn into that horseshoe, even if technically it satisfies all the other conditions. Those are what I would recommend for the next 2 steps to get you to a really intelligent snake game. This already is pretty solid AI, and it's far more enjoyable to watch than just creating an AI that's going to map through it. And I think it requires a little more coding know-how and actual like critical thinking than just importing a module that's going to put a bot, put an agent into your code. But you can tell just from watching it and playing it on your own, this is not a completed project. But I think with what we've talked about and what you've learned in this tutorial, this would be a really good spot for me to stop, suggest you take it the extra step, and let me know in the comments if you got further, if you found an improvement, or if you really would like to see more, if you'd like to see me take this project the next couple steps. Let me know about in the comments below. If there's enough interest, then I definitely can make a follow-up to this video where I show you how you would make the kind of things where you'd avoid turning into a dead end. You would be able to make decisions that would turn to the left and right and use the boundaries. Because obviously right now you can see the snake is never going to voluntarily turn to go through the left or right or up or down boundaries because we haven't told it how to calculate that that's actually the fastest route. So I hope you found this enjoyable. Again, I really appreciate likes on the video, subscribes to the channel, kind comments, great feedback. All that stuff helps me out a ton. I really enjoy doing these YouTube videos, and the support makes it possible. So thank you so much. Be sure to let me know if there's anything else you'd like to see in the future, or if you have any comments. As always, good luck with your projects, and thanks for watching. Thanks. Bye.